Muito boa tarde a todos. Vamos aguardar mais 3 minutos para dar início à reunião. Já vi que já temos aqui bastante pessoas na sala e já temos conosco os dois oradores que eu passo a apresentar. Temos primeiro o Bruno Lobo, que é gestor de atividade na saint-Gobain. É o gestor da atividade de construção modular, industrializada e 3D. E temos o professor Ian Cosney, da Universidade de Massachusetts, que é um especialista em materiais de mudança de fase e que vai fazer, digamos, a sua intervenção, dar conta do seu vasto saber nesta área, após a intervenção do colega Bruno. Vamos aguardar mais 2 minutos apenas. We're going to wait 2 more minutes to begin. Esperamos mais 1 minuto apenas. Se quiserem, entretanto, colocar questões, poderão colocar, agora não no início, né? Mas poderão colocá-lo através do chat da reunião. Muito bem, já temos a sala bastante composta. Esperamos só mais alguns segundos. Muito bem, vamos então dar início. Eu passo a palavra então ao meu colega Bruno Lobo. E passo então a palavra e o Bruno, de seguida, a sua apresentação passará ao professor Ian Cosney. Muito obrigado pela vossa presença.
Muito boa tarde a todos. Penso que já estejam a ver o meu ecrã. Antes de mais, agradecer-lhes a presença em mais este webinar integrado na Academia Saint-Gobain. Eu vou fazer aqui, apresentar aqui um projeto que temos em parceria com a Universidade de Aveiro e outros parceiros para contextualizar apenas um pouco o que vai ser a intervenção do professor Cosney logo de seguida à minha. Portanto, este webinar tem como foco a inércia térmica em sistemas de construção leve com recurso a novos materiais. Este é o tal projeto Thermacor, da qual somos parceiros, que foi desenvolvido pela Universidade de Aveiro e que consiste em, o objetivo deste projeto será o de avaliar a eficiência térmica de painéis PCM macroencapsulados na eficiência térmica e na inércia térmica deste tipo de construções. Como disse, eu vou só contextualizar um pouco o tema para depois o nosso convidado, o professor Ian Cosney, definir aqui um bocadinho mais em termos de soluções deste tipo de materiais. Portanto, aqui apenas um pequeno enquadramento que eu vou fazer então agora ao projeto e às soluções que foram usadas. Este projeto consistiu e consiste ainda, que ainda não terminou, na construção de 2 células de teste de tamanho real, em que usaram a mesma solução construtiva, cerca de 5,5 metros de largura, 5,5 metros de profundidade e 5,5 metros de altura. Ambas estas células foram instaladas no mesmo local, como podem ver na imagem à direita, exatamente com a mesma orientação solar, apenas afastadas entre si para que uma não tivesse qualquer efeito de sombreamento sobre a outra com a orientação solar em questão implantadas. O sistema estrutural é o mesmo, assim como o isolamento térmico da fachada e da cobertura, com a exceção de que uma das células tem os tais painéis PCM, enquanto que a outra não tem. Aqui vamos nos focar um pouco nas soluções saint-gobain que foram integradas neste projeto. A estrutura destas duas células de teste é uma estrutura em LSF que foi revestida exteriormente com umas placas Glass Rock X Load Bearing, placas estruturais e com certificação estrutural para este tipo de sistemas, em que foram desenvolvidas idealmente e com resistência para zonas úmidas e zonas exteriores. Portanto, o contacto com a água para a placa em si, mesmo sem qualquer tipo de tratamento especial adicional, não é um problema. No interior foram usadas placas hábito, que são placas também de gesso laminado, mas que são aditivadas no seu processo de fabrico, de modo a lhe conferir capacidade estrutural. Ou seja, a combinação destas duas placas, por dentro e por fora da estrutura LSF, conferem estabilidade a esta estrutura. Ao nível dos pavimentos, foi usada uma solução compósita de painéis USB e a solução Solera Rigidur, que é composta por duas placas Rigidur solidarizadas entre si, de modo a conferir melhor propriedades térmicas, importante para o piso térreo, e também propriedades a nível de acústica. No exterior, e para complementar a fachada, foi usado o sistema Weber Therm-Comfort, que foi constituído, portanto, pela placa Glass Rock X Load Bearing, mencionada anteriormente, um barramento, uma colagem feita no Weber Therm Pro. Posteriormente foi colocada uma lã mineral, lã de vidro de alta densidade, Weber Therm Clima 34 de 60 mm, complementado o barramento armado também com Weber Therm Pro e Weber Therm Red normal, e antes de dado o acabamento em Weber Plus Decor Plus foi aplicada uma camada de Weber Prime regulador. De referir novamente que esta solução foi aplicada nas duas células, portanto, exatamente a mesma coisa para podermos comparar os resultados. Os envidraçados foram realizados com caixilharia de alumínio, com corte térmico e com vidro saint-gobain, com uma emissividade de 1.0 e um fator solar de 0.22. Ao nível da cobertura, foi também realizada uma solução híbrida, portanto, seguindo o mesmo racional do pavimento, foram usados painéis USB, juntamente com a Glass Rock X Load Bearing, que é uma continuação da fachada, e posteriormente foram colocados painéis de rocha IXO 40 mm, que são os painéis que já vêm preparados com uma emulsão que permite a aplicação direta de membranas bituminosas para fazer a impermeabilização da cobertura. Portanto, aqui os painéis que acabei de referir. O resultado final da cobertura, aqui podemos ver duas fases. Na célula da direita vemos ainda a fase de aplicação final das placas IXO, enquanto que na célula do lado esquerdo já temos a cobertura concluída e devidamente impermeabilizada. Ao nível da envolvente interior, todas as paredes e tetos foram finalizadas com placas hábito, sendo que, como referi anteriormente, uma das células foi revestida com estes painéis PCM, que era um dos objetivos do teste. Tal como pelo exterior, pelo interior, as células de teste são iguais, com as mesmas divisões, colocadas com a mesma disposição, apenas a única diferença, volto a referir, são os painéis PCM. aqui um aspecto da solução exterior. Portanto, aqui é possível ver o aspecto com que ficou a solução Weber Thermoconfort, revestida com o Weber Decor Plus. E pronto, e agora vou passar a palavra ao professor Ian Cosney, que vai esmiuçar aqui um bocadinho do tema da inércia térmica neste tipo de sistemas. Professor, now it's your turn.
Thank you very much. I really appreciate the invitation. Sorry, I'm not speaking in Portuguese. Didn't have enough time in my life to learn yet, but maybe at some time I will learn. I must say at the beginning that that's great pleasure to be invited into the Saint-Gobain related project, because in my life in the United States, I've been involved in many projects together with Saint-Gobain. We had several projects focused on thermal insulations. We had also several projects focused on both wall and roofing systems. So actually, this is a very nice view and a nice opportunity to be part of that activity here in Portugal, when you guys have wonderful climate conditions combined right now with the super advanced thermal testing facility for buildings. And I am quite positive after seeing that facility and working with my colleagues from University of Aveiro that pretty soon that facility will be well known, because I think that they will be able to demonstrate advantages of the thermal mass and phase change materials. As well, I think that at close future, they will be able to advance the path how to Portuguese buildings can to go into zero energy space conditioning, just achieving zero energy without most of the energy coming from mechanical systems, which can be very unique and actually very important considering situation in Europe, which we have right now. So let me go to my presentation, and I would like to share my slides. Let me see if this will work. Screen. How to do this? PowerPoint energy thermal storage. Because I don't see my slides. Okay, let me do this that way. I have opened those slides, but unfortunately, I cannot. I don't see them, so I have to go a different way. Really apologize. Okay. Okay, do you see my slides?
Not yet.
Not yet, they are coming, I think. Huh. PowerPoint Live. It's telling me that it's loading my presentation. Okay.
Something
do you see this?
Okay. Yes,
okay.
Now we can see it.
I really apologize for that delay, but in different countries, the systems work in different way. So that's it looks like. So I would like to talk today in a short way about the need for well-directed and well-designed building energy storage technologies in US buildings, but please don't take it just directly, not only in US buildings, just in buildings general. And I would like to make sure that I will give you some advanced information, how this information can be implemented into Portugal buildings. This is the outline of the presentation which I'll be talking about. I will start from conventional systems and talking about how conventional systems have been used in the past. Then we will go to phase change materials. I will give a little bit theoretical introduction. Cannot do too much because we have very limited time. I will show some test results which should help you understand how powerful phase change material system can be in buildings. And I also will discuss a little bit about, I call this designer's dilemma. That means that what to use, how to use, against which systems you have to make the choice, and the reason why, for example, phase change materials can be better choice than other systems. So let's start. We know very well that our ancestors have been using thermal mass for centuries, and actually they have been using this successfully. So you don't have to go too far. You can go to several heavy stone buildings in Portugal, and you can see that actually going to church or castles, you can see that even in the hottest summer day, you go inside and there's comfortable temperature inside the buildings. I was, when I was teaching back in Europe, I was giving my example to my students when I was saying, okay, you have to go to Notre Dame Cathedral in Paris, which is actually in reconstruction right now, and see this during the very hot summer day, and you can come during the very cold winter day. And you could see that actually temperature is almost identical. More important, even if these people would try to heat that building during the winter days, it'll be completely uneconomical, because to move that huge thermal mass into the higher energy level, it will take a lot of energy. But it is also a good thing, because if you, in the summer day, it is not that easy to move that temperature up because of the heat coming from the outside. So we can see several examples coming from the stone construction, but it used to be adobe construction, which we see here in Aveiro a lot. We can see also a lot of solid wood construction. So there are many different ways how to build out of natural materials and having advantage of thermal mass. Moving to the next slide, you could see that actually people have been using thermal mass and phase change materials for generation as well. This is the first phase change material house, which have been built, I don't know where, but long time in history. And you could see there's a generation of people up north have been using this construction successfully with acceptable thermal comfort conditions. Now I would like to show the building, which is really first phase change material building built ever. This is building built by Maria Telkes, a professor of Massachusetts Institute of Technology in 1941. In early 1940s, she analyzed climate of Massachusetts, and she figured out that actually during the 60 years time period, there was only the longest time period without sun, 9 days. So she designed a mount of PCM in that building to provide enough heat for 9 days without sun. And actually that building worked very well, providing 100% of the energy for heating of the building. It's a great message for you guys in Portugal. Comparing climate in Massachusetts and in Portugal, it's just, just there are two different classes. You have much better conditions and much more sun. So actually looking for that perspective. And if you could see, this is combination of thermal mass, phase change thermal mass, and solar design. If you go and use those advantages in Portugal, it's a message that we can easily achieve the state of the zero energy construction without adding into too much expenses. So remember, this was 1994. 1941, 42, 43. 3 years, 3 winters, 100% of provided energy for the building. I would like to tell a little bit right now about what is the thermal mass and see what is the conventional thermal mass against what is the phase change thermal mass. So let's start from explanation how thermal mass works. You could see on the chart on the right-hand side, there are 2 lines that more fluctuating line is the line which we call solar thermal temperature. So this is actually temperature of the wall or the roof under the solar conditions. So we have sunny day and temperature of the roof is going up. Temperature of the wall is also going up. During the night, the temperature is going down. Then the other line is showing what our building is seeing on the internal surface, either of the roof or wall. And what we can see that actually that fluctuation on temperature is significantly lower. How much lower it is depends on the amount of insulation and the amount of thermal mass. What's the major important fact to remember from those charts is that actually we can reduce the peak of that thermal signal, I would say. Let's call this, some people, engineers are calling this thermal load. And then we can also, if you can see, we can move that peak of the maximum load right side, yes? That means that instead of having, for example, peak at 1:00 p.m., we can have that peak of the thermal load about 3 p.m. This is very important, and you will see in further slides that actually in the national policy situation, when you have millions of people trying to use air conditioning and at the same air conditioning units at the same time of the day, maybe not healthy situation for energy grid and the power companies, we have the tool to manipulate with that peak load. Please remember that in most developed countries, buildings are representing about 40% of energy consumption. And I assume that, I don't know exactly the number from Portugal, but I assume that number is similar here. I would like to spend a little bit time about explaining to you what is PCM, phase change material. And again, let's go to the example. Let's imagine that we have 2 glasses of Coke. 1 glass of Coke is without ice. Another glass of the Coke is with ice. And we are walking at street in the middle of the summer with 35 degrees Celsius or 40 degrees Celsius. After 15 minutes, maybe half an hour, we try to drink Coke from one hand and from the other one. Imagine which one will be more pleasant to drink. That one with ice. Now imagine we have a roofing insulation or roofing design, and one roof is without that extra ice. Let's call this ice, it is phase change material. Another one is with phase change material. And in the middle of the summer, we have temperature of that roof without phase change material rising up rapidly, following the sun moving through the sky. Quite early at the morning, 10 o'clock, we have already temperature going up. And building is seeing this. Most of commercial buildings are using air conditioning, and they will have to react to that temperature increase. The other building with that ice, what we call PCM, that PCM, which is not melting at 0 degrees Celsius, melting at, for example, 30 degrees Celsius, it's standing at the same temperature. And this is 10 o'clock, the same temperature, 11 o'clock, the same temperature, 1 o'clock, the same temperature, 1:30, we are moving up. So what is this? Depends on the design we can buy time, and we can have time which can actually be used to help the whole industry, whole power industry in the country, just to go over the peak load in the country. Very important, remember, buildings are representing about 40% of energy consumption for the whole country, the huge power. How important it is. I give you example of different designs, different building assemblies, and you have that blue one. It is just another example of that solar temperature. And then we have several lines showing lightweight structure, and then structures red and purple. There are structures with more or less heavy thermal mass. And actually, you can see that actually with heavy thermal mass, you can go to the point that building is not seeing that thermal fluctuation. Very important. And actually, that's what, being here in Aveiro, I see Adobe houses. This is what is design, original design of Adobe's. If you have enough thick Adobe house wall, you can actually get to that effect. On the right side, I am showing the real test results from the roof advanced designed by me. When I compare conventional roof, similar what we have in the buildings in Aveiro, on those test buildings, what it was showed before my presentation, against building roofs with phase change materials, specially designed those roofs. And you could see that actually black line is showing the thermal fluctuation on the conventional design roof. The other one is just that pink one is showing how far we can go with design of PCM. And you could see the statistics, the line that actually we can reduce the peak load by 92%. It is just for one day, but it is easy to do 90–95% in that range for the whole summer. So this is achievable. That's matter only in using proper materials and proper technique, proper design. Just to those people who will ask me a question, okay, you have different R value or different U value of those roofs. No, steady state U value in all those experiments was exactly the same. Next slide is showing that people have been using phase change materials for several decades, and I give examples of the different systems. So there is one starting from the left. We can see that actually there is the ceiling application. We can see in the middle the application of that sprayed fiberglass, that white stuff going onto the wall. On top of this, we see the panels similar like has been used in Aveiro, but if those panels are non-metal, they are plastic and filled with organic PCM. And another important product on top, it is one of the gypsum board product, which has been known around the world for many years and used with more or less success, depends on design. And depends on the material used in that phase change material used in that board around the world, probably 1,000 applications. And we can see also one of the applications when somebody is using phase change material as a part of the fenestration system. So talking about phase change materials and thermal mass, I would like to sell to you a little bit information about advantages. And actually, in the past, I've been doing phase change materials for several decades. In the past, everybody was looking for energy savings. Right now, we are going to significantly different challenges and significantly different way of applications of phase change materials. This is the schematic of the building. When I try to show you how many building operational loads are dynamic. And you could see actually the whole building is a very dynamic thing. So, you know, just space conditioning, energy conditioning are very dynamic things. And, you know, just they have been known to building scientists for decades. But what we have right now, we have coming solar system, renewable energy systems, which are extremely dynamic. And we have electric mobility, electric cars, which are another group of very dynamic. And interesting fact about electric mobility is that they are coming with huge capacity for energy storage. Yes, because cars are coming with batteries. On the other side, we have grid, electric power grid, which is another very much dynamic component. And in all this dynamic environment, phase change material can play a very important role. Here is how important that role is. And I call this DAC chart, and my colleagues in the United States have been calling this for almost a decade that way. That chart was drawn many years ago in my colleagues in the state of California, when they figured out that actually for the energy consumption, typical energy consumption for the building, when you can see on the top on the top chart that thicker black line. We have in each average building, we have like two major peaks. One morning peak, it's about 7 o'clock to 9 o'clock. Then everything with energy is going on almost leveled situation. And then we have huge peak about 3 o'clock to 7 o'clock. Those peaks, if we look like, they create some situation when our energy system has to be designed against. Our power supply systems are not designed for average energy supply. They are usually designed for the peak energy supply. And if that peak is going up significantly, we have to add simply the additional capacity to produce in each country. And also we need to add additional capacity to transmit that power, deliver that power to users. This is very significant expense to each nation, and each nation is trying to just minimize those peaks. So how we can minimize those peaks? Energy efficiency, thermal insulation, and as I showed in previous slides, through using of PCM. But this is another big factor. We have also renewable energy coming, and that renewable energy coming are making that belly in that bird. So we have several lines you can see going down and down and down. There are several specific years listed in California when solar power was added to the power grid. Solar power systems are usually used and owned by private investors. So those guys are willing always to have maximum benefit of their investment. That means that they would like to produce as much power as possible. But then we are coming to conflicting interests. Why? Because if we create that belly in that bird, because simply we are adding negative power to the grid, our power plants will have to be turned off because there will be too much power on the grid. This is not possible because if you turn off a power plant, that it will take a week or several days to put this on the grid. So the solution is that actually simply government will have to turn off photovoltaic, which is unacceptable for private investors, yes? So what we need to do, we need to find a way to store this energy and move that belly to different time. The best would be to move that belly in the time when we have a peak, yes, afternoon peak. So this chart is showing how important it is to have thermal storage and energy storage capabilities. Several states and several nations around the world are trying to build up different types of the energy storage facility just to lessen that big belly and make it smaller and also move it to the later time. You have on the bottom side, on the right side, you have similar chart developed, I think that in China or in India. So this is not only United States situation. That situation is typical for many different countries. And it is very, very important to have capability to store energy. Doesn't matter if this is electric power or if this is thermal power, because as I said, in buildings, we can manipulate with those loads, and buildings are representing 40% of the whole energy portfolio in developed countries. So moving forward, I would like to discuss a little bit about thermal storage capabilities. And actually, I would like to give you an example how important thermal storage capabilities can be. I took the example of Empire State Building, and actually, if you calculate all concrete in Empire State Building and all steel in Empire State Building, and if you assume that you have delta T of 5 degrees Celsius or 10 degrees Celsius, you can figure out that actually if you make the simple calculation, just amount of the mass, what you have in that building, then density, and then heat capacity, and you will see that actually the total heat capacity of the building is just tremendously high, and it is about 369 thousand kilowatt hours for 10 degrees, and 150 for 327 kilowatt hours for 5 degrees, assuming that temperature change will go through 5 degrees. Now let's compare this to something. And I did comparison to the Tesla Powerwall batteries. Each Tesla Powerwall battery, which is the system which Tesla is selling with their solar systems around the world, has about 7 kilowatt hour of the solar power. So imagine that for 10 degrees difference, temperature difference process, the whole Empire State Building is equivalent to over almost 53,000 of Tesla batteries. If we assume smaller, 5 degrees, which actually most colleagues in analysis around the world are using 10 degrees analysis. So we have 26,000 of the Tesla batteries. This is the capacity of the thermal storage capacity of that building. Of course, we can ask ourselves question, how well this energy is available, and so far, yes, I agree. But actually ask yourself question also, how many buildings like this we have in each country? How many concrete buildings? How many multi-story buildings? How many shopping malls we have? This is huge capacity which can be used just to help the whole economy, energy economy for developed countries, and not only developed countries. We have also, we can assume that actually we have millions of residential buildings, and in the US, 60% of energy consumption in building sector is coming from residential buildings, 40% from commercial buildings. I don't know what is that situation in Portugal, but probably the magnitude may be 50-50 or some kind of similar. Imagine that each building in the US, residential building, average residential building in the US weight between 50 to 80 metric tons of the materials. It's mostly concrete, wood, and some other materials, which can be considered as a thermal storage options for if well designed. So now I would like to talk a little bit about designer's dilemma, what to use. Conventional thermal mass, phase change materials, or maybe going into easiest way, battery storage. So let's ask ourselves how much energy stored in specific material costs. And I don't want to go through all calculations. If somebody asked me, I can send that presentation, but you could see that actually there is a $52 to $104 per kilowatt hour stored in that concrete masonry unit. If we go to wood, we have also cost, which is between $55 to $111 per kilowatt hours of stored thermal energy. If we go to conventional thermal material, which is, I use paraffinic materials here, it is between $138 to $160 per kilowatt hour of stored thermal energy. Now let's go to something which all industries, and actually I've been reading news today, day before, that was the news about companies working on batteries, that new company for Volkswagen. So everything is just this is probably one of the most busy businesses. But look, in this case, kilowatt hour, stored kilowatt hour it's about $273 per kilowatt hour. So this is more than two times more than for phase change materials, and 3, 4, 5 times more than for conventional building materials. Question is, how much of the batteries and how much lithium we can use? And you could see actually devastation of the environment in case of the lithium production. We can tolerate as human beings in the future, and how much energy will be able to effectively saved during those lithium batteries, considering that we will have increased demand for energy storage in the future. And actually, there is another picture telling what will be the consequences. And I would like to give you a comparison of the cost of the recycling. Recycling of the concrete, and this is US California state data, it's between 60 cents to $25 per ton, depends on where this concrete is coming from and how it is used. Then a recycling of wood is about $24 per ton. Recycling of phase change material and paraffin is just the cost of production of new products, and actually it is very difficult to estimate, but that paraffin doesn't have to be recycled, can serve more and more for new generation of the products. And when you go to the recycling of the lithium batteries, there are many different estimates, and I don't want to be off, but I put just a range of the cost, which has been listed by several agencies, and I gave the references. It's between $1,000 to $2,000. People there are some optimistic people saying that they can go below 1,000, but in general, conclusion is that actually, even though we have ability to recycle batteries, it takes 28 batteries to make a single new one, And a lot of agencies are still considering this as not cost effective. It has to be subsidized highly by governments in different countries. So I would like to move on to the second engineer's dilemma, how to place thermal mass within the building. And this is a very important question. We had discussion with University of Porto and University of Aveiro, and they asked me, okay, how about that PCM? And I said, there is no a PCM. This is the specific PCM for specific application. That's the reason why we have so many failed project demonstration of PCM around the world, is that people have been trying to use a PCM. PCM is not a solution for any problem, energy problem in buildings. PCM has to be designed well. And actually the same way, like you cannot say, oh, give me that beam and I will cover that, use it for that bridge. It never goes that way. It has to be, engineer has to come and calculate what has to be the specific cross section of that beam, what kind of materials, and how long that beam can be, just to support maximum load, what we are talking about. The same as with PCMs. PCMs, they have to be designed, well designed, the same way like other engineering issues. If we will not design, we will have another group of failures. How important is placement of thermal mass in buildings? Let me give you that simplest possible example. Let's imagine that we have concrete wall insulated with thermal insulation. And we have on the first drawing up on the top, we have thermal insulation on the exterior side. And on the other part below, we have thermal insulation, which is pink or orange. It's on the interior side. But we can see that actually, I am showing you just the value of thermal inertia, thermal constant for that specific assemble, and we can see that for the first case when we have thermal mass facing interior of the building, we have thermal time constant. We have about 43. If we have insulation facing interior of the building, time constant is 7. That means that just that simple switch of material is changing time constant of like in magnitude like 6 times. It's something too good to realize. And actually, there's the first conclusion. If we want to use thermal mass effect, let's put that thermal mass inside of the facing interior. If we don't, who cares? But we may have some penalties, energy penalties. And actually, this is a very good example how important is that placement. I show you simulations of small residential house, single-story house, when actually we did simulation for several locations across the US in different climates, and this is average data for different locations. And you can see actually that definitely system with the thermal mass facing interior and thermal mass, another one with insulation being placed inside the whole assembly, are significantly better than other systems. We can make many justification, and actually codes in most countries are not giving credit for that placement of thermal mass. But good designers should know about this, and good designer should have at least explanation to potential client that placing insulation on the interior may not be the best choice. Another thing, and I gave the specific example of phase change material application, is showing how important it can be also in usage of the phase change material placement in attic application. Again, we have 3 scenarios. Scenario when we have thermal mass facing interior, thermal mass placed between the layers of insulation, and thermal mass facing attic. And you could see that actually they are not very big numbers, but energy savings are between 7% and almost 8%, almost nothing. And that almost nothing is for the case when insulation is facing attic. That means that thermal mass is facing attic. That means that in the most effective are systems when, again, we have thermal mass that, in this case, red line showing PCM is facing interior of the building. I would like to conclude, because we have limited time, with this short summary. telling you that actually if we start to talk about environment and we would like to use our resources in the most effective way, we try to also start understand those systems which we are designing better. And to better design those systems, we need to incorporate building dynamics. Current situation, political situation in Europe, and also the energy consumption situation may force us to better use dynamic building systems. And I showed you that actually, if we implement dynamic components of the building in the right way, we can shave those peaks of energy and we can shift those peaks of energy to different time. With different designers and different mechanical system designers tried to do this, and actually it was called big success. Somebody could shift that energy peak using conventional mechanical systems by half an hour. With thermal mass, it is easy to shift that peak 4 hours. I designed several systems, and actually I can shift that thermal peak even more than 8 hours. So this is possible. And actually my major message is, remember, just try to understand dynamics of the building. The dynamics of the buildings can be very helpful. And actually we need to start seriously thinking about our environment. Without good knowledge about building dynamics and opportunities to use different materials than chemically, environmentally polluting materials used in some energy storage systems, maybe that extra possibility may be very important for a lot of economies around the world. That would be all on me, and I really appreciate again that invitation. It was great pleasure talking to you guys, and here is my email address if somebody would like to send me question, or I'm not sure if I can answer question right now for you guys. Thank you.
Thank you very much, Professor Jan Kosny. I will let our guests to put some questions if they want. Alguma questão que queiram colocar? Aqui é uma questão do... É uma pessoa com a mão levantada. Eu vou dar a palavra. Paulo Ferreira. Muito boa tarde. Pode colocar a sua questão.
Boa tarde. Penso que estarão a ouvir-me neste momento.
Sim, estamos sim.
Sim, ótimo. So the question is for Professor Jan. I had a doubt on your presentation because if I understood well, this idea of profiting or taking profit of the thermal dynamics of the building to change the peak hours of energy demand, but what about the time that the users are awake? So, for example, if we have a peak of energy demand on, for example, 8 p.m., people are awake, and even if the building transfers the peak demand for example, 3-4 a.m., because then the heat is more, well, is higher, people are sleeping. So how do you see this change of peak energy demand with the normal daily daily usual the daily activities of the people that have more or less a time frame?
Actually, it's a very good question, and actually, if I understood this well, yes, this is something like I would say phase change material and thermal mass are just engineering tools. And you can use them in many different ways. If you want to move that peak, and you can move this. If you want just to shave the peak, you can shave it. So this is the way how we engineers need to understand what are consequences of using those materials, and we need to try to implement them in the best, most effective way. I understand that actually in many buildings in Portugal, people are not using air conditioning, for example. So that would be very valid for in your case when you say, okay, people are coming to bed, and then you will have huge heat wave coming to for those people, and just they may not sleep well. Perfectly no, but it is just a matter of designing this, and that's why I several times highlighted that actually good education for engineers in designers in this area is necessary, because as I said, you can just manipulate that peak time in the way that you will just reduce the amount of the peak, but you don't have to shift this. If you want to shift this, you can shift this half an hour, or just shift this number of hours, which will be convenient to you. So this is up to designer. Also, energy from the building can be thermally saved in many different ways. It can be saved directly in the envelope, but also can be harvested and saved on different way. And you can, for example, take roofing energy. You have a lot of sun energy and convert this of heating, for example, hot water. Commercial buildings would be different. So this is, that's why I said it has to be different design for each of the users.
Thank you very much, Professor Ian Cosney. Any more questions? Há mais questões que queiram colocar? Well, I think there is no more questions. There are no more questions. Bruno, se quiseres dar uma última palavra.
Resta-me agradecer a presença do professor Ian. Professor, thank you very much for joining for this session. It was very, very helpful to understand this thematic. I had the opportunity to have a longer conversation with Professor before. That was also very nice. So thank you for both. And if any of the participants will have some questions later, they can also reach us, me and Carlos, if it's related to solutions, to the Thermacor project. You can always contact us. Thank you very much.
There is one more question. Bruno, mais uma questão. Eu vou dar a palavra à participante Marina. Just one more question. Marina, estamos a ouvi-la. Arquiteta Marina Santequeiro. Pode colocar a sua questão?
She is muted, so she has unmuted herself.
Now you can hear me, right?
Yes.
Just to say about our experience in Portugal. In fact, usually with older buildings, adobe, renders, stone masonry, or even brick. When we have enough mass, we do feel the effect of the thermal inertia. Usually the older buildings give us that. From the 50s back, we have that. And the delay of the peaks is just the feeling, because I am from the south of Portugal. It's very hot, and we have renders and other buildings. So I have the experience of living in them, and it really it's very pleasant because it softens the temperature inside the building. So whether it's for housing or commercial buildings, services, whatever, an office, whatever it is, along the 24 hours of the day, it is always pleasant because it's soft. It slows down the transitions of temperature. And that, just for that, it makes it very pleasant, saves us energy, and it becomes pleasant. We hardly have to turn on a heater or a cooler. Or we do it a lot less, as long as we are careful enough to close windows and doors, of course, and we have the proper insulation. But it is, and I am very pleased. I wrote it on the comments. I'm very thankful for Saint-Gobain for bringing up this issue, because when I do calculation, and whenever I hear about thermal calculation, thermal inertia is usually forgotten or minimized, or I don't know. I'm very pleased because you bring this up. In hot climates mainly, I think it's very, very important. Maybe cold climates don't realize this, but hot climates do, definitely. And south of Portugal is one example. Thank you very much.
I very appreciate what you say. I agree.
Well, if there is no more questions, não havendo mais questões, vamos terminar. Thank you, Professor Ian Cosney. Thank you again.
Great pleasure.
E estejam atentos aos próximos webinars. Este foi o último webinar antes das férias, antes dos meses de verão. E retomaremos em setembro com novos temas que esperemos que sejam do vosso agrado. Muito obrigado.
Thank you.
Obrigado a todos. Boa tarde.